Today we're going to talk about implicit differentiation. So we have been able to differentiate functions that are solved for y explicitly. Okay, so now we want to consider functions of the type x squared minus 2y cubed plus 4y is equal to 2. So implicit differentiation happens whenever you have x and y on the same side or they're mixed in with the equation and you cannot separate them. So this is where we do implicit differentiation. Now we've actually been doing this already, but we just haven't explicitly said so. If I have y equals x squared, so if I take the derivative with respect to x, well, the derivative of y is 1, and then the dy dx is equal to 2x dx dx. Okay, so the dx dx, that actually turns into 1. But this dy dx, that's what we know as y prime. So we've actually been doing this all along, but we just haven't actually written it out. Okay, so some basic facts to consider whenever we're doing implicit differentiation. Realize differentiation is taking place with respect to x. So we are using x as our variable. However, if you look at this third point here, if you take the derivative of y with respect to x, you get dy dx. If you take the derivative of x with respect to x, you get 1. This is the dx dx. Okay? So when you differentiate terms involving x alone, you can differentiate as usual. When you differentiate terms involving y, you must apply the chain rule, and that's where we tack on that dy dx. So rule of thumb is anytime you take a derivative involving y, just tack on a dy dx after it. Okay? So we are going to look at some examples here. So differentiate both sides with respect to x, obey the chain rule, multiplying dy dx every time you differentiate an expression containing y. Anytime you take a derivative of y, just tack on dy dx. Then you will isolate dy dx by getting all of the terms on one side of the equation and all other ones on the other side. Okay, so let's actually see this put into place. If I'm looking at example 1 and I need to find dy dx, that means I need to differentiate. If you look at that guy right there, those two values are multiplied. Because it's x and y, we have to do product rule. So product rule is the first times the derivative of the second. Well, the derivative of y is 1, and just remember that we need dy dx after every time we differentiate y. So I have the first times the derivative of the second plus the second times the derivative of the first. Plus, now derivative of y again is 1, but I need to obey the chain rule and tack on a dy dx. And the derivative of 8 is 0. So now I need to find dy dx. What I'm going to do is I'm going to get all of my values that involve dy dx on one side and everything else on the other. So I have x dy dx plus dy dx is equal to negative y. I can factor out dy dx. I would get x plus 1 is equal to negative y, and then divide. So that is my equation for my derivative. Now it needs to be at x equals, or at 3, 2. So My y value is 2, my x value is 3, so I get negative 2 over 4, or negative 1/2. Now let's look at example 2. So we have x plus 3xy minus 2y squared is equal to 2. And we need to find the derivative at 1, 1. So again, we do have a product rule here, the 3xy. So we are going to differentiate. So take the derivative of each piece. The derivative of x is 1, plus now the 3xy. The first times the derivative of the second, plus the second times the derivative of the first. So that's your product rule. Minus, now the derivative of 2y squared is 4y, and then remember you need dy dx after it. And the derivative of 2 is 0. So again, keep all dy dx's on one side and move everything else over. So we have 3x dy dx minus 4y dy dx is equal to negative 1 minus 3y. So factor out dy dx. You get 3x minus 4y. And then you can divide. So we get negative 1 minus 3y over 3x minus 4y. And again, we want this derivative at the point 1, 1. So we plug in 1 for x and y. So we would get negative 1 minus 3 over 3 minus 4. So that is negative 4 over negative 1, which is positive 4. So now let's look at example 3. So it says find dy dx. Not at a coordinate point, we're just finding the derivative. So implicitly, derivative of y cubed would be 3y squared dy dx plus 10y dy dx minus 5 dy dx minus 2x is equal to 0. Again, get everything on one side that does not have a dy dx. I'm going to do 2 steps in one here. I am going to factor out dy dx, so I get 3y squared plus 10y minus 5 is equal to positive 2x. Now I can divide, and I get 2x over 3y squared plus 10y minus 5. Looking at example 4, it says find y prime. Same thing as dy dx. If you look at this y e to the x, that requires a product rule because we have a y and an x being multiplied. The 3 pi here, that is a constant. So keep that in mind. So if I do product rule, I have the first times the derivative of the second plus the second times the derivative of the first is equal to 0. So now just isolate dy dx. So e to the x dy dx is equal to negative y e to the x. Dy dx is going to equal negative y e to the x divided by e to the x. Those will cancel, and dy dx is equal to negative y. Now let's look at example 5. Differentiate cosine xy is equal to x plus 3y. So cosine of xy, this one is going to require an actual chain rule. So derivative of the outside, the derivative of cosine is negative sine, you leave the inside alone, times the derivative of the inside. Well, the derivative of xy, that requires product rule. So the first times the derivative of the second plus the second times the derivative of the first. Equals, the derivative of x is 1, the derivative of 3y is 3 dy dx. Again, get all dy dx on one side. You can actually distribute this one. So you will have to distribute the negative sign. So you get negative x. There's a dy dx in there. Minus y sine of x y is equal to 1 plus 3 dy dx. So now I'm going to get all of my dy dx's on one side and everything else on the other. So I have negative x dy dx sine of xy minus 3 dy dx is equal to 1 plus y sine of xy. Factor out your dy dx. You get negative x sine of xy minus 3 is equal to 1 plus y sine of xy. Divide, you get dy dx is equal to 1 plus y sine of xy over negative x sine of xy minus 3. That one's a little tough, but we did it. Now looking at example 6, differentiate the natural log of xy is equal to sine of x. If you remember, the derivative of a natural log is 1 over whatever's inside the natural log. In this case, because what's inside the natural log is a product, we will have to use chain rule and product rule. So the derivative of the natural log of xy is 1 over xy times the derivative of the inside. So the derivative of xy, again, product rule, so you have the first times the derivative of the second plus the second times the derivative of the first. And this is equal to the sine, derivative of sine is cosine x. So I am going to multiply on both sides by xy. So I have x dy dx plus y is equal to xy cosine x. Now we just subtract y. So I have x dy dx is equal to xy cosine x minus y. And then last but not least, divide by x on both sides. You get xy cosine of x minus y all over x. So example 7, so given this ellipses, find the equation of the tangent line at x equals negative 1, 2. So remember, to find the equation of the tangent line, you need pot and sot. We already have our point here, negative 1, 2, so we just need the slope. To get the slope, we need the derivative. So if you take the derivative of that formula up there, you would get 2x minus, you need a product rule there, so make sure you put that in parentheses. So you have the first times the derivative of the second plus the second times the derivative of the first plus 2y dy dx is equal to 0. Distribute in that negative there. You will get 2x minus x dy dx minus y plus 2y dy dx equals 0. Factor out dy dx and move everything else over. You will get dy dx times negative x plus 2y is equal to y minus 2x. Divide to get dy dx by itself. You will get y minus 2x divided by 2y minus x. Now you need to plug in the point -1, 2. Running out of room here, so dy dx. So y is 2, x is -1. There's a 2 there. And you will get 4/5. So your tangent line is y equals 4/5 x plus 1 plus 2. Now it says find the equation of the normal line. Remember that normal is perpendicular, so we need to take this slope and find the opposite reciprocal. So the normal line would be y equals -5/4 x plus 1 plus 2. So we can actually calculate higher order derivatives using implicit differentiation. There is a substitution process that will take place here, but we are going to be doing implicit differentiation. So find the second derivative given cosine y is equal to x. So if we take the derivative of cosine, that is negative sine y, and then don't forget, anytime you take the derivative of y, you need to tack on a dy dx, is equal to the derivative of x is 1. So dy dx is equal to -1 over sine of y. So that is my first derivative. To get the second derivative, I do this process again. Now I'm going to write this as negative sine y to the negative first. So if I want the second derivative, I do a chain rule here. So I take the -1 and I drop it down in front, which would give me a positive. So I will have sine y to the -2nd, and then the derivative of the inside. So the derivative of sine is cosine y, and then I do need to tack on a dy dx. Now, this is where the substitution happens. This dy dx, we already know what it is. It's -1 over sine y. So that's where the substitution will happen. So sine y to the -2nd is sine squared y in the denominator. I have cosine y in the numerator times dy dx, which is -1 over sine y. So I can plug in another value here. Actually, let me simplify this just a little bit more here. So we have cosine y over, or I'm going to have a negative there, negative cosine y over sine cubed y. Another substitution is going to happen right here. Cosine y, we know that that equals x. So the second derivative is actually -x over sine cubed of y. All right, last example. Find the points at which the graph of this ellipses has either a horizontal or vertical tangent line. If we have a horizontal tangent line, it means that dy dx is equal to 0. If it's a vertical tangent line, that means that it's undefined, the derivative. So first things first, we have to find the derivative. So if I take the derivative of that function up there, I would get 2x plus this xy requires a product rule. So you have the first times the derivative of the second plus the second times the derivative of the first plus, and then the derivative of y squared is 2y dy dx equals 0. For some reason, that derivative of a constant always gets forgotten. So anything that does not have a dy dx can move over, and I will factor out a dy dx. So I get x plus 2y is equal to negative 2x plus y. Divide, and you will get dy dx is equal to negative 2x plus y divided by x plus 2y. Now I'm looking at two different points here. I'm looking where dy dx is equal to 0. If the derivative is equal to 0, that means the numerator is equal to 0. So I would get 2x plus y is equal to 0, which means that y equals negative 2x. I can plug in this value into my original equation to get x. So x squared plus x times negative 2x plus negative 2x squared is equal to 27. Simplify this all down, you will get 3x squared is equal to 27, which means that x squared is equal to 9, which means that x is equal to plus or minus 3. So on this ellipses, we have horizontal tangent lines at x equals plus and minus 3, which if you look very closely, that is a horizontal tangent right there, and again right there. So the horizontal tangent happens at negative 3, 6 and 3, negative 6. So now we look at our second point where dy dx is undefined. If a function is undefined, that means that the denominator equals 0. So in this case, we would have x plus 2y is equal to 0, which means that y would equal negative 1/2 x. I can substitute this value into the original equation, so I get x squared plus x times negative 1/2 x plus negative 1/2 x quantity squared is equal to 27. Simplify this all down, you will get 3/4 x squared is equal to 27, which means that x squared is equal to 36, which means that x is equal to plus or minus 6, which if you look on your ellipses here, the tangent lines at these points are in fact vertical. So these coordinate points are negative 6, 3 and 6, negative 3. So implicit differentiation, it can be really confusing to begin with, but just always remember whenever you are taking the derivative involving a y value, you just need to tack on dy dx.